want to start out just going through like the various different types of isomers. There's this tree, and obviously, like I'm sure you can figure out the tree pretty easily, but it's just a somewhat sensible way to talk about some of the more nuanced or complicated features of the various different kinds of isomers. So whenever you say isomer, what's the definition of an isomer, and like what are the two major types?
They will have the same molecular formula,
Mhm.
but not necessarily the same structure. And
Okay.
the two different types, funny enough, are structural ones and stereo
Okay.
isomers.
Nice. Yeah. So structural or constitutional, but I mean, it's the same thing, right? So yeah, that's perfect. Okay. And then and stereoisomer. So what's the primary, like if you, how would you crystallize what the difference is between constitutional or structural isomers versus stereoisomers?
Structural have that um, same molecular formula,
Okay.
which is just, I guess, like the standard isomer because that's all
Right.
that they share. And then stereo isomers, I think there are different kinds, but they so that's where like the tree branches off. But um they can share the same structure or connectivity.
Okay. Yeah. Yeah, exactly. So it's like, yeah, like constitutional isomers or structural isomers are going to have different functional groups even, so they just have like the same numbers of atoms and that's
Hmm.
really all they have in common. So I guess they would also have, barring a lot of different functional groups, like if they had were relatively devoid of functional groups, they may have similar physical properties, but even their physical properties are going to be off, right? Because it's the functional groups that determine all of the physical properties in, like a molecule. And so, uh, but so what about stereoisomers? Like, what would you expect with regard to their physical properties? And what do I even mean by that? What are physical properties?
Physical properties are
If that's a stupid
characteristics
question.
of a molecule.
Okay.
Characteristics of a molecule. So it's something that doesn't change, like the boiling point or
Okay.
whatnot.
Yeah. Yeah. Exactly.
Um,
Yeah.
yeah. And what was the first one? What do I expect from stereoisomers?
Yeah. Yeah. So constitutional isomers will have different physical properties, right? Because they have different functional groups. Versus stereoisomers, what would you expect to be able to, I don't know, say about their physical properties?
Oh, sure. I guess I mean, if they're like arranged in the same way or like share the same bond conformations or positioning, then it would make sense that they would share physical properties as well to some extent.
Right. Yeah. They are more similar than the physical properties would be for structural isomers. So what are the two major types of stereoisomers then? I don't really
Um,
like the way that they've defined this in this book, but whatever. So
is it like conformational and
yeah,
non-conformational?
yeah. Or it's conformational versus configurational. So which is kind of annoying, but yeah, conformational versus configurational. Uh Honestly, that's really dumb. But and so why do you think I'm saying that that's dumb? Like what's my problem with this? I mean, that's a terrible question, but I
Besides
think
them
you can
sounding
probably figure it
super
out.
similar.
Yeah, well, so
um,
my biggest issue with it is that isomers are different molecules, right? I mean, that's,
okay.
we're saying they have the same like empirical formula, same molecular formula, but they're not the same molecule. And
Mhm.
obviously that's the case with the structural isomers. Stereoisomers are going to have more in common. And so configurational isomers, they are definitely different molecules, but conformational isomers are the same damn thing. Like they're the same molecule. They're literally the same molecule. And so that's why I don't love the definition that they've given you of that here, or that they've even put it in the isomer tree is kind of the problem I have with it. I think they wanted to teach it and didn't have another good place to put it, so they shoved it into this tree. Because so do you understand what I'm saying by that? That they are actually the same molecule, different
Yes.
conformational isomers.
Yes.
Okay. meaning that,
they're just rotated a little bit in space, but they're literally the same.
right, exactly. Yeah. So you can, it's not like one of the configurational types, you can't rotate around that bond that that we would be referring to. Versus, but the conformational isomers you can, and so yeah, they're actually the same molecule. I mean, it does take a little bit of energy to interconvert them. Sure, if there's a bunch of steric hindrance, then it takes a little bit more, but they are the same thing. So I don't love it, but anyway, I just wanted to really emphasize that. So and then there's all these various different like configuration, or I guess it wouldn't be configurations, but all these various different conformations that these things take, like the anti the anti-staggered. I just turned the page and saw one of them, as well as like the eclipse conformations. And so I don't, unless you want to go into all of those, I don't really care to like dive that deep into specifics because we've got other stuff to talk about. But just so you're aware, those are the various different.
On that note, just to clarify, is the biggest takeaway from that more so like the energy state of those configurations? Oh my god, I just choked, sorry.
Oh, you're fine.
Rather than like the configurations themselves, I guess.
Yeah, I would say, I would say that understanding like which of these molecules you're most likely to find in nature, I guess, and they are the same molecule, but which configuration. Just understanding the various energy differences between them, and understand the idea, like obviously to interconvert between two molecules that are this identical and that are in the same conformation is zero energy, right? Because they're actually the same thing. And then to interconvert between like the furthest isomer away from that would be the structural isomers. You have to move a bunch of stuff around. It'd probably take a ton of energy. And just know that the conformational isomers, technically, I suppose they do require some energy input to interconvert, because you have to get past you're going from one relative minimum on an energy graph to another relative minimum. You have to cross over a local maximum in order to get there. So just so you're aware of it. But I've now discussed it far more than it deserves.
Got it. We can move on.
Yeah. Right. So then configurational isomers, what are the two major types of configurational isomers? Because this is where we get more nuance, and this is where it's like what we actually want to be discussing, because this is very high yield, this stuff, for some reason.
Chirality?
Okay, so chirality.
So like chiral versus achiral?
Okay, yeah. So it depends on if a molecule's chiral, then it can, or if a molecule has a chiral center in it, then it can have configurational isomers, right? But it's not like you could have a molecule that's chiral and another one that's not, and those be isomers of one another. You see what I'm saying?
Yes.
Yeah, because to be chiral, you just have to have, like, I'll just draw like this central carbon with 1, 2, 3, 4 things around it. And so like if that's chiral, then it would have a configurational isomer of that might have 2, 1, 3, 4, like that. And so they both have to be chiral, versus like if these were all 1, then that's not chiral. But then it's also the same molecule. So anyway, so there are two things that you can identify in a molecule to know that it will have configurational isomers. And so the first one is chirality. What's the second one?
The second one, besides chirality, I'm not sure. Besides chirality, is it?
So I'm just looking at I really don't like the way they made this tree. I apologize for referencing you to this book. So the other way that you can be a configuration or have a configurational isomer is the like E versus Z or cis versus trans arrangement.
Oh, right.
Yeah. And so I don't know why they put that like down. I mean, I guess technically, sure, those are diastereomers, whatever. I would still like it if they put it up higher, whatever. But they made their table in a different way than I would. So who cares? I'm just gonna write cis trans because I think that's a little bit easier to reference anyway. But just make sure you're aware of which one's which. Do you know which one's which? Which is cis E or is trans E?
Ah, shit.
On
Cis is E.
Dang it. I was gonna say it's the other way around, but I'm
Maybe.
not 100. I'm only like 80% sure, and that's not very sure. I'm probably more like 70% sure.
Wait, no. E is opposite.
Right.
So
Yeah.
Z is same.
Yeah. That is
Oh,
true.
sorry,
Okay.
I cheated for that answer.
Oh no, you're fine. No, I was hoping you would find it because I was just like, I think it's that way, but I'm not completely sure. So yeah, we'd say like Z. So I guess I should say trans cis and cis because EZ sounds way better than ZE, whatever. Okay, so that's just the other way that you can have configurational isomers. I think that is pretty self-explanatory. Whereas the chirality can lead to a lot of different complicated scenarios. So, but really quickly before we get off of the EZ thing completely, what would you expect about with regard to the physical and chemical properties, specifically of easy isomers of one another? So for instance, I don't know, maybe you have a molecule. It's like, I mean, you're going to have a double bond. And so we'll just say this is just an H, whereas this is like CH2, CH3, and this is an H, and this is, I don't know, also CH2, CH3. So what's the difference between that and, like it's isomer?
It being the same.
Yeah. In terms of like their chemical and physical properties, what are some things you would predict from this?
I think the E version, so trans, would be seemingly more stable.
Okay.
And
More
because
stable in
like
what way?
well, because those functional groups are far closer together in the Z configuration.
Okay.
And
Oh, okay. So you're saying it's like that this is like this is like a lower energy form of the molecule. So
yeah,
like that these two might have some steric hindrance between this. I agree with
yes.
that completely. Yeah, I agree with that. I didn't realize what you were saying at first, but yeah, that's a really good point.
Steric hindrance is the word I forgot for it, but yes.
Yeah. You'll remember it after today. That's like the name of so much of this. It's just
True.
like steric. Yeah. Yeah, so that's a really good point. So maybe, like if you were to be undergoing some synthesis and there's a probability you could end up with the cis isomer or the trans isomer, you might expect that you end up with more of the trans isomer, just in our hypothetical synthesis that we haven't given a name for because I don't really know exactly where you would start. I mean,
Right.
it depends on your starting stuff. We could figure it out, but and so what about like the melting point of these things?
The melting point would supposedly be higher for E, but lower for Z. If there's like, or rather, if there's more steric hindrance, it would be a higher melting point. So never mind.
You said higher for E and lower for Z. Is that what you said?
Higher for Z, lower for E.
Okay. That is true. Yes, that is true. I had to
Yeah,
think
I
through it for a second. Yeah.
flip-flopped in my mind.
Yeah. And so why is that? Why do you think that?
Apart from steric hindrance, it would be no, it's not the
And yeah, and this molecule is not a great one to see it with because it is a relatively small molecule. The really potent example of this that I should have maybe drawn if I thought about it before is like a long chain fatty acid or something. And so obviously
Mhm.
like the long chain fatty acids that look like this, obviously they have the carboxylic acid at the end, but these have the highest melting point of all of the long chain fatty acids. Whereas once we start throwing double bonds in on these things, they sorry, it just started a siren going off. Once we start throwing double bonds in on these things, they can start really deviating dramatically in their melting point in particular. And so
Mhm.
like here, this double bond is going to mess things up a little bit. My screen just turned off. Okay, it's back. Thank God. All right.
Mm.
So a double bond where you have like the trans setup can mess things up a little bit, but in one dimension of the plane, or in one plane at least, it will remain relatively the same. And so while it's not going to be able to pack on its friends as well as say this one could, because the reason this has the highest melting point of all of the all of the fatty acids that are of the same length is because you can just they lay down on top of each other really nicely. And so there's a lot of like
Mhm.
van der Waal interactions between the chains that just lay down right on top of each other. And so once you start throwing double bonds in, you kind of mess that up, but it tends to mess it up way more if you have a cis double bond than if you have a trans double bond. And so the so the cis versions of the molecule will tend to have a little bit lower melting points than the trans versions do. And
Okay.
now I'm trying to remember which one you said was which in in your answer, because I always think of cis trans rather than easy. And see, the reason I just wanted to make sure I illustrate why. So like if we make this cis, then I'd probably need to scoot it down actually. So if we make this, if we say we put it in at that same spot that we put in the other one. So right here, if we have to make this a cis bond, then the thing is going to have to come off of the same side, right? And so you're going to get this really weird, you're going to get this really weird thing where you've got like, all right, so here's our bond again, just like the other
And
one,
has to go.
but now you've got to go the other direction pretty much. And so now you're going like this. And so that's just doesn't really lay down very nicely at all. You see, because these are both like
Mhm.
on
Mhm.
this side of the bond, and the hydrogens are off this way. And so this is obviously just like a not at super duper accurate representation. I'm drawing in 2 dimensions rather than the tetrahedral structures, but you can actually imagine just like one hydrogen coming off of each of these peaks. You can imagine that these two are both in the plane of the page, and this one's like coming slightly up and out, and this one's going like slightly down and in, or vice versa. And so you can imagine it as a tetrahedral thing, and so the actual 3D molecule could all line up in this plane as you've drawn it here. So these sorts of drawings end up being a lot better than like for instance that that kind of thing. Just FYI for if you're trying to think through some of these problems and represent things in space to yourself. But anyway, so yeah, the cis double bonds will have lower melting points because it just takes less energy to overcome their terrible intermolecular interactions, because they have 90-degree angles in them pretty much. So
Cool.
does that make
Okay.
sense? Okay.
Yeah, no, that
All right.
makes sense.
Okay. Okay, cool. All right, so that is probably good for the E and Z stuff. What about the the chiral isomers? Molecules that are isomers of one another because they're chiral, like this one.
They're
What
mirror
would you expect?
images.
Okay, yeah, so they're mirror images. What does that mean actually, though?
It means that they can't be definition of mirror, you can't like overlay them. They use like the
Okay.
handedness example. So like they're the same, but they can't they're they can't be overlaid.
Yeah, so which way should I rotate this in order to make it to where these two are directly across from one another like a mirror? Like see, because like if I were to say, okay, yeah, here's a mirror, and so
Mhm.
here are they mirror images here? No, not really, not at
Mm-mm.
all. So So, but there is a way that you can orient it to where they will become mirror images. So how could you do that? Like, where's your mirror need to be? How do we need to rotate it? Because we can rotate this thing too. See, I think I can anyway. I'm just guessing.
I mean, you could rotate it technically either way, but I would say clockwise.
Rotate it clockwise. So like 45 degrees to this way, like that. And like that.
No. I'm like, can I pick it up and just go like this?
I just was because this way it looked like it was saying clockwise, but like that. I don't know. This didn't work out as well as I thought it would. Never mind.
Actually, that almost worked, I think. Where you just were.
Right here?
Right?
Yeah.
Yeah, now
Exactly.
It can go.
Yeah, perfect. Yeah, because now the threes are lined up with each other, both out of the page. The 4 is going back into the page. And the fact that I drew it, the fact that it's drawn down here, that is literally no different than if I drew it coming out this way. That's the same thing. Because whenever you're assigning those priorities, you ignore the one that goes into the page. Yeah, and then the 2 and the 1 are obviously identical as well. So yeah, perfect. Cool. So yeah, that's kind of like a way to illustrate the mirror image idea. But because I feel like this is one of the hardest concepts for people, is really being able to look at a 2D representation of a molecule and just know whether it's is or isn't an enantiomer. Now I can't get it back where it was. This is there we go. Okay. So all right. So what would you expect with regard to the chemical and physical properties on these things?
I think they'd be the same.
Okay.
Yeah, chiral.
Do what?
If they're chiral, they are expected to be the same.
Yeah. So they have like the same, molecular weight. So that's going to tell you but all of isomers do. So insofar as you're looking at molecular weight, but like higher molecular weight generally means higher melting point, higher boiling point. And so obviously that's the same. But then they also sit up in the same way in 3-dimensional space. It's just flipped over. And so they will also have about the same reactivity with other molecules as well, because versus like even the EZ isomers, this is something that I didn't illustrate, but even the EZ isomers, like these are going to, this one and its mirror image would react slightly, or not its mirror image, but the version of it where we've got this down here and then this gone. Those two are going to react very differently. Why does this molecule react differently than this one? If you're like, I don't know, if you're attacking it with a nucleo or with an electrophile, for instance.
Sorry, I think your screen just lagged for a second, but which one were you pointing to?
Oh, sorry. I was saying like, so I'm changing these two groups around.
Got you. Yeah.
Oh no. Dang it, why did it do that? Okay, yeah. So I was just like going back and forth between that and oops, whatever. My example's gone because I had the undo redo going back and alternating back and forth. So
okay.
But I was basically just taking this and moving it down here to alternate between cis and trans.
Gotcha.
And the point was to say that like cis trans isomers, I guess I could just in all that I could have just drawn it, but these will have actually quite different reactivity whenever it comes to, like, for instance, an electrophile coming in and attacking, because so if an electrophile is going to attack an alkene, then it's obviously going to come in and want to grab the electrons off of that double bond. That's really the only reasonable spot. And so it could do that really easily in this cis isomer that we have, assuming these are both hydrogens, and this is hydrogen, this is hydrogen. It does it really well in the cis isomer, but it's a little bit from one side in particular, but it's a little bit more difficult on the trans isomer. And so you don't have like an obvious side. And so you're going to get different products in. So while you have like pretty similar physical properties, you get somewhat different chemical properties, meaning
Got
like
you.
when they undergo chemical reactions, you get different products. But
Okay.
and so the chiral molecules will kind of orient the same way in 3D space, because it doesn't
Mhm.
matter like if we say like 2 is really big, and so it's causing a bunch of steric hindrance, it doesn't matter whether we flip it places with 1 or not, it's still going to be able to be attacked the same way because it will be able to orient in the same direction, more or less. I mean, as the same way that your hands can. However, there is one specific instance where they will have vastly different chemical properties. And by they, I mean like enantiomers.
Mhm.
And so what is that? What kind of a reaction would need to occur for 2 enantiomers to have very, very different chemical properties, very different reactivities?
Oh. What kind of reaction would occur?
I'm looking around. A good example here. Oh, I found one. That's funny. So so if I were to take so if I take both of my hands, which are enantiomers of one another, and you are the one that said that, and I put this ball in either hand, it reacts the same way with both hands, right? Like it can do all the
Mhm.
same stuff with my right hand that it can with my left hand. However,
Mhm.
if I take and so in reactions like that, hang on a sec, the screen is kind of laggy. If in reactions like that, they're going to have exactly the same chemical properties, and that's going to be most reactions. However, whenever you are reacting in an environment that looks like this, so you can't see my hand right now, but if I take my hand and place my right hand and place it down on this, it matches up perfectly. I mean, you could do it with your hand. You take your right hand and
Mhm.
place it over this hand that's on my screen, and it matches up
Mhm.
perfectly. So they react the same way, right? But if you take your left hand and lay it down, it doesn't. And
Right.
so, and so enantiomers, or molecules that have opposite configurations at one or more chiral centers, are going to have identical chemical properties except in chiral environments. And then their chemical properties are going to be totally different from one another.
Oh, okay.
So it's like hands interact with most of the world, like pretty similarly, right versus left, except things like gloves.
Yeah.
Yeah. Yeah. So, or like, I don't know, like socks go on both of your feet, but shoes don't, because socks aren't chiral, shoes are.
It's gonna stick with me for a while. Oh God.
That's a good one. Yeah.
No, that's a good one.
I'm gonna pat myself on the back for that one. Anyway, and so the reason that I'm emphasizing this so strongly is because it's really important. Because think about like drug design, or like any drug you give to a patient at all. The body itself is like human physiology, not just humans, all physiology is
Mhm.
inherently extremely chiral. There's very, very little space in like at the molecular level where we aren't chiral. And
Hmm.
so as you may have noticed in Ochem lab at some point, or maybe you didn't. Did you take Ochem lab during the pandemic?
No, I
Or
took
were you
Ochem
done?
lab beforehand. I
Okay.
took biochem in the pandemic. That
Oh,
was
nice.
weird.
Yeah, I mean, I didn't do any labs, and so I did Ochem
Also,
lab, and I
physics
did the
lab.
labs I had to. I hated
Physics
physics
lab,
lab.
dropping like apples on a screen to learn was the highlight of my college career.
That's funny. So they still made you guys do the labs, just like
Yeah,
at
and it
home and
was
stuff?
maybe the stupidest. No, the funniest part is that they tried doing like an interactive version, but it just failed on so many people's computers that all they did was record, like the professor would go in, record himself doing the lab, and then tell us to watch it and write a report on it. And it was maybe, I learned nothing.
Honestly,
No
like
one learned anything.
I would have learned more. I think that I would have liked that more because I hated labs so much. Because I would always like, I don't know, I just felt like I could never I'm a very slow worker, and so I felt like I could never just like get the work done to my liking in the time that was available. And so I think I would have loved it that way, because then I would have just been like, yeah, this is just like regular school. I like this. I mean, insofar as you're gonna like writing a report on anything, but yeah. So anyway, one thing that you probably did observe in Ochem lab though is that racemic mixtures. Do you know what a racemic mixture is?
Sorry, do you hear yelling? Sorry.
Do what?
Sorry, do you hear yelling in the background?
Oh no, I don't.
My
I've got
dog is
this.
going crazy.
I've got this AI thing set up to where like I can't hear any like ambient noise in your on your end, and you can't really on my end either. Like I
Okay.
can like sit here and bang on my keyboard like this. Can you hear me typing at all right now?
No.
Yeah, and I'm just like smashing my keyboard. So
Oh God.
yeah.
Wait,
it's
give me
kinda
2
nice.
seconds. Let me mute for a second.
Okay.
Sorry, we have a puppy and he goes rampant sometimes.
Oh, you're fine. Yeah, don't worry about
Okay.
it. Because I literally don't hear it at all. But so, but if you need to go deal with it, then you can, because I know
No, it's
sure it'd be
okay.
a
It's okay
distraction.
now. I was just slightly concerned.
Okay. All right. Yeah. So what I was saying is that okay, so do you know, okay, I remember now. The question was, do you know what a racemic mixture is? Like what is a racemic mixture?
Oh man, that was a while ago. But that's when those like isomers are in equal concentration within a mixture,
Yeah,
right?
exactly. Yeah, for sure. Yep. Yeah. Yeah.
Okay.
So it's like you
And
do some synthesis reaction for this whatever, like this C123, we'll call it C1234 molecule,
yeah.
and you get like 50-50 for R and S of that molecule. So 50-50 R versus S. Versus, you have like a pure R or a pure S compound. And so separating out a racemic mixture is like one of the most time consuming, resource consuming things you can do in an Ochem lab.
Mm-hmm.
And so it is very, very much in the interest of all pharmaceutical companies to be able to market racemic mixtures
Mm-hmm.
as drugs, rather than getting the I can't think of the word, getting the optically pure compound. That's what I was looking for, optically
Okay.
pure. Yeah, because they rotate the plane polarized light. And so like if you can, so pharma companies have done this over and over and over again throughout history. They will discover like either the R or the S version of some compound in nature. They probably found the compound messing with fungus or something like that, and they'll discover that one of the enantiomers has properties that are medicinally valuable. And rather than go through the extra cost of separating it out, because that would make it cost them way, way more, they just send it to market as a racemic mixture. But because our bodies, and we'll talk about why in a second, because our bodies are inherently extremely chiral, just because like one isomer does one thing doesn't mean you know anything about what the other isomer is going to do for optically active drugs. And so there have been like tons and tons of really bad scenarios where there will be like one mildly beneficial isomer, and the other one is just like incredibly toxic and kills a lot of people.
Oh,
And
beautiful.
so yeah, exactly. Yeah, and so, but most of the time, for the vast majority of the time, it turns out to be fine, because the one that's optically, or the one that does have the desired effect, will have its effect, and then the enantiomer of that thing will just be inactive totally. So like ibuprofen, for instance, is a racemic mixture of whatever the molecule's name is, and the one of the isomers is just pretty much completely inactive. And yeah, and so there's a little while where they started, some drug company decided to purify it and just market the pharmacologically active one. And when they did, they had all these issues of people bleeding out because it was too active, because everybody thought, oh, it's basically just like ibuprofen. I can just take 800 milligrams of it. And then they would. And that's like taking 2000 milligrams of it. And so they, people, and one of the side effects of too much, I can't think of what the name of the molecule is. It's driving me nuts, but too much of whatever that is, cyclooxygenase inhibitor, will make it to where you just start bleeding out of like every orifice. And so that happened for a bit. So just FYI. Yeah. So what about our biology makes us so necessarily chiral? Because most molecules you run into, like nature loves symmetry. So most spaces and things and stuff you look at have a degree of symmetry. So why is like every molecular space that we have more or less chiral? And you do know the answer to this. You just probably don't know that you know. Or maybe you do. I don't know. I doubt it says in the book, but this is something that they test a lot.
No. Interesting. Okay. I feel like that makes sense in terms of like enzymes or whatever, because you want things like, or that's just the example I'm going with in my head, at least. Not
no, but it's right. Yeah, it's exactly right.
Because you want to be specific, or like our bodies need to be specific in order to, certain molecules do certain things or whatnot, but not so specific that it inhibits any like other functions.
Yeah, I see what you're saying. That's a really good point, because specificity is definitely part of, it's definitely very important if you're making a biological organism, because if you have a receptor that has a agonist that looks a certain way, but it also binds something else really well that's present all the time, then that doesn't work out very well. And so, the high degree of specificity probably is like, I hadn't thought about that, but it probably is like very, very evolutionarily significant. So that is as good an answer as any, but the answer that they will test on this is that it's not necessarily like I haven't heard that mentioned, the specificity thing, but it absolutely has to be true the more I think about it. So what they're going to test here is they're going to require you to take like a reductionist approach, because you don't really know that much about any individual enzyme, I'm assuming. I mean, maybe there are a few enzymes that you know some stuff about because you studied them in undergrad at some point, but like even like after med school, I don't know that many enzymes. And I mean, I know a bunch, but not that many and not that much about them. However, I do know a lot about what makes up enzymes. So what makes up an enzyme? Like, what is an enzyme exactly?
Protein.
Okay. Yeah. So what makes up a protein?
Amino acids.
Okay. So what's an amino acid look like? Like, walk me through the structure of an amino acid, just like a general one.
It's got carboxyl group.
Okay. So you've got a carboxyl group.
An amino group.
Okay.
And then it's got something else depending on which one it is.
Okay. Yeah. So you've got a carboxyl group. You've got an amino group. In between them, they are linked with a carbon. And this carbon in between them, in most of the amino acids, will have an R group and a hydrogen. So this carbon is chiral, right?
Right.
And so this is the basic building block of basically every single drug target ever. Because think about what do drugs do? Well, they act on enzymes, because enzymes are like the leverage points for getting stuff to happen the way you want it to happen in vivo. Right. So and so if the basic building block, if every single one of the basic building blocks for every single one of the things that actually matters for a drug is chiral, then the thing itself matters. Well, almost necessarily has to be chiral, right? Yeah, because it's not the whole enzyme that the drug's going to interact with either. It's just like a few tiny residues in the active site. And so
Right.
those residues will have so the active site will have a chiral character, a handedness to it, because every amino acid that is present in that active site is itself chiral. So that's why. And so that's one of their favorite. That's probably the most important concept in at least this chapter, for sure this chapter, but I don't know about maybe the whole Ochem reading that you did, just because they love to test that kind of stuff. So I'm tempted. I'm going to come back to the amino acid. This would be a perfect transition over to the biochem stuff, but I
was ready for
want
it.
to, yeah, I do want to say a couple more things about the isomers, because this is pretty relevant. So, because the last thing we haven't talked about yet is the scenario where a compound has multiple chiral centers. Okay, so because we talked
Right.
about one chiral center where they're just opposite configurations around that one. What if you have two chiral centers and you have opposite configurations around just one of the two?
What happens?
Or what do you call that, I guess?
Oh, oh boy. It's a version of diastereomers that are called.
Oh no, that's the answer. It's
Oh,
diastereomers. I was just trying to make one up, but yeah, yeah, okay.
Never mind. Okay.
Yeah. Okay, yeah.
There are
So
specific versions of diastereomers now.
yeah, there are specific
I
versions of
couldn't
them.
remember.
That's fair. Okay. So what's the specific version
No.
of it?
Meso.
Okay, so that's a different sort of thing, kind of. That has
Never
that's more to
mind.
do with the meso compounds have more to do with whether there is an internal plane of symmetry in the molecule itself. So
Oh,
like half of the molecule could fold over on top of the other half. I'm trying to find if they have a
okay.
picture of one in here. Let's see. Do they really not have a picture of this? I could have sworn they had pictures of this stuff. Whatever. Anyway, so yeah, so meso compound doesn't even necessarily have to have a chiral center in it. It just has to have an internal plane of symmetry. It's
Okay.
on, well, I guess you have a very different version of the book than I do. So the example that they give is so there's tartaric acid, which is, so you draw it out as like the COOH, obviously, and then the Fisher projection version, you've got the OHH, and then so you have two different types of tartaric acid that are isomers of one another. One of them is this one on the right. I don't know why it has to be on the right, but that's what I'm doing. It's just called D tartaric acid. Whatever, I'm just gonna say tar. Whereas the other one, wish I wouldn't have written that there. How? Whereas the other one is called meso tartaric acid. And the reason for this one being I should have made you guess which one was which, but the reason this one's called meso, whereas this one's just D, it's not nearly as cool of a name, has everything to do with the fact that the one on the left, the meso one, has this internal plane of symmetry through the molecule, to where, see, like if you just draw this blue line through both of them, I guess, even this one, the one that's meso, can fold over perfectly on top of itself, whereas the one that's not can't. And so that's why.
Okay.
Yeah.
Cool.
Yeah. Anyway, that's why. It doesn't make sense though why you can't just rotate around that single bond, because I was just
It
ranting
doesn't
about
have. It's a sigma bond. It doesn't have that ability. Or like, right? Sigma bonds can't just rotate like that.
Oh, that's all they can. That's the only bonds they can. Right. So because all
I
single
thought it
bonds are
was
sigma bonds.
Yeah.
It's the pi bonds that
Oh,
can't
it's the
rotate.
pi bonds can't rotate. Oh, never mind. I
Mhm.
mixed it up.
Oh, you're fine. So do you
Okay.
remember I want to illustrate like why that is the case really quick, just because it'll make
Yeah.
it make a lot of sense. And so this is back from day one. I'm just stealing this picture that I drew, so I don't have to draw it again. So I think you probably do remember that picture. I'm just gonna draw it again, or I'm just not gonna draw it again. I'm going to copy it, paste. I just don't want to mess it all up. I'm very OCD about whatever. I'll delete it. So this is a group of p orbitals, right? Remember that I told you you have like px, py, and pz of the p orbitals. And so
Yes.
whenever you talk about a compound having or a molecule being sp3 hybridized, because the S was here, this red, right? When you talk about a compound being sp3 hybridized, that's because it is going to be sharing electrons back and forth with another atom that might be over here and have the exact same scenario where it's got its own orbitals. And so they will reach out to one another in a way that requires these orbitals to take on a certain amount of S and a certain amount of P character, because if the electrons are being shared back and forth, it doesn't make sense that any electrons are just going to stay right here around the nucleus. They're all going to have to come out here to be shared back and to be shared between atoms. I couldn't think of and so it's going to be, so whenever you sp3 hybridize something, it basically just means that you've got 4 clouds coming off of it, and the sp3 comes from the fact that you've got 1 s cloud and 3 p clouds that go into these. And so any given orbital at that point has like 3 parts p character and 1 part s character. All right, anyway, point being that the ones that that just has to do with the ones that are actually being shared between the two. Those are the ones that will take on the sp3 hybrid orbital. And so the ones that aren't sharing electrons with any other thing are just going to remain as p or pi orbitals here. Okay. And so a pi bond is formed whenever you get a double bond between two things, right? And so if you have a double bond between 2 atoms, you no longer are sp3 hybridized, you're sp2 hybridized, right? Okay. And that's because once you have that double bond, only 2 of the 3 p orbitals that were going to be involved are now involved in the hybridization of that orbital. So we'll just say that we've got px and pz are both going to be involved in forming that sp2 orbital, right? Because we could only take 2 to form the sp2. And so there's this third p orbital that is the py that is just left over hanging out all by itself. And so those are the ones that actually share the electrons involved in that second bond in a double bond. And so you talk about sigma bonds and pi bonds. The sigma bonds are stronger because it's a more significant interaction to share the electrons across that hybridized orbital, that hybridized cloud. Whereas the pi bonds are a lot weaker because they're literally just like overlapping way up here, sort of like off the side of the stage. They're like not super, I don't know, the interaction is just not as strong. However, the reason you can't rotate around a pi bond is because, or around a double bond, is because if you take this one, let's say we'll just take this one on the right here, because say that we're sharing 2 electrons here, and then we've got our 2 electrons down here as well. And so we take the one on the left and just try to flip it, try to rotate it to where it's down here. Now we're sharing electrons across this way. And that's just like really, really far. And so you necessarily have to break that pi bond in order to rotate around the double bond. Anyway, yeah. So that is that just to give you like understanding of why pi bonds are pi bonds, sigma bonds are sigma bonds. Sigma bonds have S character in them, hence the S and the sigma, and pi bonds have only P character or only pi character. So that's and that's something that like I felt like I never understood until I just kind of had to figure it out myself. So I just kind of teach people just so you have some like, I don't know, background for why you need to know that, or the fact that it's not just purely arbitrary, even though this seems quite arbitrary. And I question whether it's even real, but that's the explanation I've come up with for it. And sorry if that's not super well thought through as I was saying it. I was trying to think it, because I've definitely explained it before, but it's not a super high yield thing. So could use some polishing for sure. All right. So the meso compound thing, I think does that make sense? Like just the fact that it has that internal plane of symmetry. Okay. And so then you're good with, so what is a definition of a diastereomer specifically? I just want to make sure you're good on that, because that's something that it also trips people up really badly.
I mean, apart from meso, which has internal like mirror imaging, diastereomers are non-mirror images, non-mirror image isomers that are like specifically configurational.
Okay. Yes. Yeah. Okay. Yeah. So they're yeah. And they classify easy isomers as diastereomers as well, which is whatever, just so you know that. But yeah, diastereomers are basically, I think that a really easy way of defining it is that they are molecules that have more than one chiral center, where not all of the chiral centers are opposite. And so, like, for instance, if we have, I'm just going to draw this molecule hypothetically speaking. Let's just say you've got here, so you've got this chiral center, and you've got this chiral center, and this chiral center for whatever. Let's just say there's.
You said not all chiral centers are same, or
so if all chiral centers are the same, then they're just the same molecule, right?
No, yeah.
Right.
What was the last part of what you said?
But so if all chiral centers are opposite, what are they? Why would
all chiral centers are opposite? It would be in like a trans configuration.
Okay, so
it would be a diastereomer.
Okay, so if all chiral centers are opposite, then they're enantiomers, right?
Oh wait, yeah, that's literally the definition of an enantiomer. Never mind.
Yeah, so if all chiral centers are opposite, they're enantiomers. If all chiral centers are the same, they're the same molecule. And so diastereomers are everything in between that. You know, like they're not all opposite, but they're also not all the same. So like if these two molecules that I just painstakingly drew here that still didn't get everything in the picture. I don't know why this copy and paste is not working. But so if you have these two molecules and we're just trying to decide what they are, like if I had R, S, and I had S, S, R, then they would be enantiomers of one another.
Okay.
You know, because these two are opposite, these two are opposite, these two are opposite, and those are the only chiral centers.
Oh, right.
All right. But if I had, rather than that, so what if I have S, R, R? So like the green one versus the blue one up there.
No, it's a diastereomer because the middle one is not opposite.
Right, exactly. So this would be one version of a diastereomer, whereas the blue one was an enantiomer. Yes. What if I do like, I don't know, S, I'm trying to now look at it and see S, R, S. So then that's also a diastereomer.
Okay, that makes sense.
Right. Okay. Yeah. So, and so for any molecule that has chiral centers in it, so for a molecule that has like N chiral centers in it, yeah, this is going to make it easier. I just give you a definition. If you have N chiral centers, then you will end up with I think it's like 2n squared minus 2 diastereomers. I have to think about that for a second. No, it's going to be something like that.
Specific.
I was just trying to give you like a really hard and fast rule, but I'm also making it up like right here on the spot.
There are 2n possible stereoisomers.
Oh, it's just 2n. Dang it.
I think it's just
okay. 2N. So then it's going to be 2n. But then it'll be 2n minus 2. I squared it. I don't know why I squared it. Because so diastereomers would just be 2n minus 2.
Okay. Right. Besides the. Why the minus 2?
Because you're subtracting this case where all of them are the same. That would be minus 1. And where they're all opposite, that would be minus 2.
Right. Okay. Okay.
Yeah. So within chiral centers, I noticed I've been writing like nothing on some of the on some of our stuff. Like the notes that I've been sending you are very bare compared to what they not frequently are.
That's
But it's
funny.
good. It
No,
means
that's
that we're
fine
going
because
quickly.
I mean you're not writing them, but like sometimes you'll say something and I'll write it.
Okay, yeah. And
Yeah,
so
so
yeah.
I have it.
Okay. I
I
just want
have
to
it
make sure
down.
that you don't think I'm just like being lazy not writing stuff, because I'm happy to do it. But there's no
No,
point in
currently my
both
version
of
is
us.
far more crowded than yours. So
Oh wow, yeah. I don't know how you
yeah.
do that. I'm terrible at taking notes and listening at the same time. Um okay, so yeah, so that is it for the stereoisomers, all that stuff. It's mostly stereoisomers. I mistakenly call this chapter stereoisomers all the time because it's really all that matters in it. The other stuff is kind of easy.
Yeah, that's fair.
And that's probably one of the higher yield things of what you covered this time. The other super duper high yield stuff is what we're about to do, which is some of the enzyme kinetic stuff. And unless you just feel like you're a monster of enzyme kinetics and you don't need any of it, I would
Wow.
recommend doing it,
I
just because.
wish I was a monster at enzyme kinetics, but I guess I'm about to be. So yeah, let's go for it.
All right, I was just grabbing my book off the shelf. I like having hard copies of books so much more.
Oh, 100. I can't read online.
Oh, good.
Either.
That
That's
makes
the
me feel
thing.
better. I've been resisting it for so long just because I'm trying to be like, you don't need to be the old person who, like doesn't can't
No,
hack it with
I am the old
all
person
level.
in class. I'm the only one with no laptop in class. I have to have
Oh, really?
handwritten
Yeah, I
notes. Yeah,
I never took a laptop to class,
which
but I didn't ever
answers your
really go to
question
I
from
didn't ever
earlier
really go
about
to
how
class
I
either.
listen.
Yeah, no, that's really good though. I mean, I feel like I think studies have actually been done that you learn stuff better if you write it than if you type it. Probably just has a lot to do with needing to be economical. And so you have to reword it rather than typing every single syllable that comes out of the professor's mouth.
Right. Yeah. Great
Okay.
at
So
transcribing though.
yeah. Yeah. So the enzyme kinetics stuff, I'm trying to find the exact right page here, is super important because I mean, obviously we talked a little bit just a second ago about why enzymes are important biologically, and I think you probably knew anyway. But they start this whole discussion of enzyme kinetics off with the Michaelis-Menten kinetics stuff. So how much do you remember from what you read about Michaelis-Menten kinetics? Or first of all, I guess start a little bit more broadly even. What do enzymes do? And
Yeah.
how do they do it? I know you know that they
Enzymes.
speed up reactions and stuff, but
Yeah, well, you took my answer. Enzymes, yeah, they speed up reactions. They're catalysts. There's different types that work specifically to catalyze specific reactions that are happening. Um, I know there's a mnemonic, but I don't remember what the mnemonic was.
I know
Um,
it.
their essential impact is on the activation energy, so they lower the activation energy and they bind to the substrate in a
Nice.
specific way
Yeah.
that depends on the enzyme.
Yeah, that works. Yeah. Perfect. Okay. Cool. Yeah. And so the specific thing is important. A lot of what they do, and I think that the best way to really think about it is you can think about like the fact that you need, say we have A and B that need to react. Okay. So,
Mhm.
and maybe A and B are two opposite ends of like a glucose molecule, for instance, or something like that. I don't know. A and B just need to react to form C. All right. So we need this reaction to happen. And this reaction, just like we talked about for kinetics in Gen Chem stuff, is going to be largely dependent on the concentrations of A and B, because in most scenarios, you're just going to have like A floating around in space, and there's going to be some A's floating around and some B's floating around, and A and B aren't going to come together until one A and one B happen to exist in the same space at the same time. Otherwise, they're just going to keep floating around in relatively empty space. And so what enzymes do is, let's say like we're looking in at this is like the enzyme's tongue. So we have its mouth open. We're just looking from top down. All right. So the enzyme will have like some A region that's shaped very much like A and some B region that's shaped very much like B. And so what the enzyme does is like a dating app for the substrates that are involved. It's
Beautiful.
just like facilitates the interaction that may not have happened as easily otherwise. I think that's a decent analogy. It's stupid, but so anyway, so that's what the enzyme generally does. And in addition, sometimes reactions will require like ATP input or something like that. And typically what that is doing is providing the energy necessary for the enzyme to shift its conformation a little bit once both substrates are actually bound, in order to make the entire process overall thermodynamically favorable. Otherwise it wouldn't happen. But not all enzymes even require ATP, because sometimes it's enough. The energy released whenever, say, like A comes in and binds to its A spot, and the B comes in and binds to its spot. Sometimes the energy given off from that is sufficient to power the conformation change in the enzyme. So it's, it depends on whether it's an ATPase or not. But you don't always have to cleave ATP. Anyway, so yeah, enzymes lower the activation energy essentially because all the activation energy is how much rate can you get out of certain concentrations of substrate. Right. So yeah. So enzymes bring that down a bit. And so what these like Michaelis-Menten kinetics are doing is really just thinking about this reaction, A plus B yields C, for a given amount of enzyme. Okay. And so the first thing that has to happen there is that you need your substrate to come and bind to the enzyme, right? And so you're going to have that reaction occurring, and it's going to be an equilibrium, obviously. Like if one of the substrates comes in and binds its spot, but B hasn't showed up yet, for instance, then A might just leave. And so you've got this reaction existing at some equilibrium. That's why they draw it with like the K1 and the K -1, because you've got some rate constant for each direction of that specific reaction. And then that forms the enzyme substrate complex. And then once that is formed is when you will inevitably go to form the enzyme product situation. And so Kcat that you'll see a little bit, you'll see it here and there, is just the rate constant, the rate law constant for that reaction from enzyme substrate complex to enzymes plus products.
Okay.
All right. Anyway, so that is some of that stuff. So for a given like amount of enzyme, because whenever we draw this plot, this Michaelis-Menten plot, the underlying assumption here is that the amount of enzyme present is constant. Right? Because it's not either of the axes. And this is something that I will harp on a lot as we do like practice MCAT passages, is the first thing you should do whenever you get a graph, whenever you see a graph, is not panic and think, shit, I don't know how to read this graph because I don't know any of this stuff, even though that still to this day is my first reaction. Even though I've done this so many times, I always just think, I don't know what this is. This sucks. I don't want to do this right now. Still. But so maybe you get like a second of that, and then you just like, okay, look at the axes and figure out what the graph is saying. Because if you just look at the axes, it's going to tell you everything that the graph is saying, right? So all we're doing here is comparing how fast this reaction is going to proceed as we add or take away substrate, right? So notice that we are not looking at time. We are not looking at enzyme. Neither of those are represented in this two-dimensional picture. We've got 2 dimensions, 1 dimension of reaction speed, the other one of substrate concentration. And so one big takeaway from this is you can tell that, and most people don't make this assessment, and so that's one reason they freak out, that this is not going to be a graph that you are able to generate from one experimental trial. You have to do a whole bunch of experiments, right? Because one experimental trial in which you throw a bunch of substrate in and see how much product is made in a certain amount of time generates like one data point on this graph. And so you have to do experiments for like every single spot on the graph in order to actually get anything meaningful. So this is like a meta graph almost. And I haven't been involved in research in a bit, so you're probably more familiar with this kind of stuff than I am, or at least more recently familiar. And so what you end up with in this graph is something that looks like this, right? So what can you, if you have this relationship, if you have this relationship, what can you say about this specific relationship between reaction velocity and substrate concentration?
It is exponential.
Okay, yeah, it's exponential initially, but then it,
And then it reaches an asymptote, which is
right,
where
yeah,
the max velocity is.
yeah, exactly, perfect. Okay, so yeah, so as substrate concentration nears infinity, the reaction velocity nears whatever this is, and so we call that Vmax. And so are you really familiar with all of this stuff right now? Should I go faster?
I'm familiar with this graph, yes.
Okay, all right. So what is it then? All right, so what's the other thing on this graph then? What is this point? Well, on the y-axis, it's 1/2 Vmax, right? Just because.
Yes, on the
halfway
y-axis
down.
is half of that, but it's important because it gives you the Km,
Yeah,
which
nice.
is the Michaelis constant, or mm.
Yeah, perfect. And so what's the Michaelis constant tell you exactly?
That's where at that point the enzyme's active sites are half full.
Okay. That's not exactly true. That's an overgeneralization people make.
Okay.
So it can be true. It depends on how relatively fast the enzyme is, honestly.
Okay.
Because it's the point at which you are producing product at the maximum rate that you could produce product. But that's not exactly the same. But and I'm not trying to be super nitpicky. I just wanted to let you know. Because you could probably get away with thinking that that's the case because there's only a small number of like super specific ways they could ask questions where that would cause you to miss it. But yeah, so it's basically just like whatever substrate concentration gets you to half of the maximum reaction velocity. So yeah, exactly. So what else could Km stand for with regard to a specific enzyme? What does Km tell you about your enzyme?
Its affinity.
Okay, nice, perfect. Yeah, it tells you how much the enzyme likes the substrate.
Mm-hmm.
Yeah, perfect. So what would be another thing that Km could tell you about an enzyme if you are led to believe that the Vmax, I guess, for a given enzyme is the same between two. Sorry, I was trying to think through how to ask this. What else does Km tell you about the enzyme if you have enzyme A and enzyme B and they both have about the same Vmax, but enzyme A has a much lower Km. So you're absolutely right, affinity, and that's still the case. But what's another thing that I could tell you?
So lower affinity would mean higher Km of that one.
Okay. Yeah, so enzyme B has
right.
a lower affinity, right? So yeah, higher
Right.
Km for the same Vmax. But since you also know their Vmaxes, you're also then able to make a comment about which enzyme is more efficient. Meaning like,
Right.
yeah.
Okay.
So if you do know something about the relative speeds, obviously, like if I tell you this enzyme has a Km here and this enzyme has a Km here, which one's more efficient? And I give you nothing about the Vmax, then you can't say anything, right? Because one of them may just have a huge Vmax and the other one might not. But if they're the same, then yeah, then Km tells you about the enzyme's efficiency. All right. So rather than enzyme A and B in that scenario, what they are likely to do is give you a scenario of like the same enzyme in both cases, but maybe in one experiment we have it at a pH of 4, and the other experiment we have it at a pH of 7.4. So in which case is Km likely to be greater? If the pH is 4 or 7.4?
4 versus 7.4. It would be greater at in a more acidic environment.
Yeah. So Yeah, maybe. So
Maybe.
that's a bad question the more I thought about it, but so your thinking is exactly right that the affinity for it's going to be lower in the more acidic environment, but you can
Mhm.
also probably predict the Vmax is going to be worse too. And
Right.
so, like if so it's kind of an asshole question honestly, but yeah, that's a bad question. Actually, it's not really because we got to talk about that. Because that's the kind of stuff the MCAT asks. I've been over time just trying to get better at asking you questions in the convoluted ways that they ask questions. Um, so anyway. All right. So the other component of this enzyme kinetic stuff that makes it harder is the Lineweaver-Burke plot. Because you seem like you actually know a lot about this. So we can blow through this quickly. Most of the time it takes a long time just to get to where we are right here.
Anything
So
that's a semi extension of math works
right.
out for me.
Yeah, that's interesting to me that you majored in something that's more closer to the humanities, I guess, than a lot of the pre-med majors are.
Yeah,
Mm.
I don't know what to tell you about
No,
that
I mean
one.
it's good. Like I think I wish that somebody would have made me major in stuff that wasn't just science, because you learn all that stuff in med school anyway. So I think it's a good idea. If I had kids, I would make them do that.
True.
Okay,
I mean, I was
so
almost. Anyways, continue.
okay, yeah, so Lineweaver-Burke plot. What's going on with this? Obviously, we have this like double reciprocal situation. So
Yeah,
you get
the fun stuff. So, um, what, what do I even say about this? So, since it's reciprocal, instead of just the graph reaching like Vmax as an asymptote, it is now the y-intercept or 1 over itself, I guess. Um,
I'm sorry, could you repeat that? I didn't catch. I didn't catch what you
oh,
said.
that's okay. Yeah. So it's because it's all reciprocal. Um, the y-axis is just going to be 1 over Vmax, and um, yeah, and the
Okay.
x-axis is 1 over Km.
You mean the y-intercept? Is that what you're saying? Or
Yeah, y-intercept. Oh my God.
okay.
Yeah.
I just wanted to make sure because that's a really so did you memorize that or do you understand why? Because that I mean nobody gets this. Most of the time when I draw this, people are like, and they just tell me exactly what everything is because they memorized it already. And so,
No, yeah, that's fair.
but I assume that you do know why, because even though nobody does, I you
I
seem
mean,
to
it goes
reason through it.
from a what's it called? And to go from I'm forgetting all of my words right now. An
Oh, it's
exponential
fine.
graph and making it linear, it has to be um reciprocal. It's the change of the equation itself.
Yeah, no, I know exactly what you're saying.
I
The
cannot put that into words though.
I totally get it. I know exactly. So the idea that, for instance, the y-intercept has to be 1 over v max. Well, that's necessarily true here, because
Mhm,
and tell me if this is what you were saying. It's
mhm.
necessarily true that the y-intercept has to be v max because we only get a y value of v max whenever we have an x value of infinity. And
Right.
so, yeah, and so if I want my x value to be, or my 1 over infinity, well, what is 1 over infinity? It's 0. And
Mhm.
so, right, and so so if my x value is 0, then that tells me that the y value corresponding to that
Has
is
to be some value.
right. Yeah, exactly. And so, yeah, perfect. Nice. So yeah, you may be the first person that I've ever worked with who like came to that conclusion that quickly too. So that's really good. Like it took me a bit of thinking through this to understand why it all works the way it does. The first time I ever taught this was for a Kaplan course, and I did not know what I was talking about. And I felt like the stupidest person ever because I thought I didn't know. And then I got up there to teach it, and I was like, yeah, I don't know what this is all about.
I mean, in class,
Um,
all they tell you is to memorize this. The only reason why I know it is because of math, not
yeah,
even
no,
because of my science classes.
no, but that's so I wish that you could understand right now how how well that bodes for your outcomes on this test. Like
Yeah.
because I mean I can sit here and tell you, but you can also think I'm full of shit. Just trying to like make you feel good. But no, like this, that is so much more valuable than a biochem PhD for the MCAT, is your ability to like understand why this is the way it is. So, all right. So then what else? You said something about KM or 1 over KM earlier.
Yeah.
What was that? Because
So
I'm
in
going
the
to be really
same,
surprised if you can tell me this.
oh
Go
my
for it.
God. If in the same vein that Vmax is reached asymptotically, Vm originally was some value on the x-axis corresponding to a point that was on like the actual curve or whatnot.
Mhm.
And this is able to give us slope, right? Because it's a linear equation.
Okay.
So from that, you're able to get Km rather than it being a result of, oh my God, my words right now, 2 points, or like not 2 points. Right, it is 2 points along the curve every single time.
Okay.
That give you like little slopes along along the
Yeah.
curve. And Vmax comes from that. And I think actually it has, is it negative? Where if if you change the equation to be linear, it has to be negative because you move it from, am I overthinking it now? Maybe.
Yes.
Okay, never mind.
Because if you think,
Ignore the last part.
because you can't have negative, right? I mean, people, the way this is going to be drawn, yes, they do that. And that's why people are able to get this right on tests sometimes, because for the most part, nobody understands it. And you will as soon as I tell you. So the way, what everybody that I ever teach this does, except you, is they will tell me immediately that the y-intercept is 1 over Vmax and that the x-intercept is -1 over Km. And I'm like, okay, congratulations, you can memorize things. Why is that the case? And nobody can tell me that, because but like if the x-intercept was really, or if this was really the way that we knew Km, then there'd be a branch of physics that I don't know about, because I don't know that we've discovered like negative like negative volumes of substrate,
Right.
like, right. So what this, so the reason, so all this is, everything left of the y-axis is just an extrapolation using like continuing the same line. Where you actually find Km on this thing, or 1 over Km, is to the right side, but it's not going to be like a nice easy thing to memorize, because because I can't say it's on a specific line, it's on neither line. However, if you remember, Km is the substrate concentration, right? Because if we look at these other graphs, Km is just a substrate concentration. And specifically, it is, so this point right here, if we were to do, like the XY coordinates for it, that the X coordinates are Km, right? And the Y coordinate is 1/2 Vmax.
Right.
Okay. So if I find the line, or find the point on this graph that corresponds to that one, it's going to be, my X coordinates are going to be 1 over Km, right? And my Y coordinates are going to be 1 over 1/2 Vmax, right? That's the same as saying 1 over Km, 2 Vmax. 2 Vmax is just double 1 Vmax. So whatever this distance is, the distance between my y-intercept and the x-axis, I just take that same distance again, right? So if we say that, so this is just another one of those same things, because this is 1 over Vmax. So now this point right here is just 2 over Vmax. See what I'm saying? Which is the same as 1 over 1/2 Vmax. And so the 1 over Km spot is just the x value at 2 over Vmax. And so you just find 1 over Vmax, which is your y-intercept. That's easy. And then go up again that same distance, and then just go over to the right until you get to a spot where you're at the, wherever you're going to be, and at the appropriate slope or whatever. It depends on what you're given, like what constraints you're given here.
Yeah.
But yeah, so it's just going to be like somewhere out in this area. And so the way that people have gotten to this idea of it being, oh, that was so close. The way people have gotten to this idea of having the Km value be like on the negative side of things is just because they memorize the extrapolation that comes off of this. But the only real data points here are in this region.
Right.
Yeah. I don't know why I got so obsessed with
Yeah, because you're not going to have like negative substrate either.
Correct. Yeah, that's what I was saying. I was just like, yeah, you're not going to have a negative volume of substrate unless there's a branch of physics I don't know about.
Okay. And at that point, Km is equal to the substrate concentration because it is at that half Vmax.
Yeah.
Okay.
Yeah, that's all Km is the substrate. Like the units of Km are molar or, like whatever are their units of concentration. Yeah, so that's all it is. So then your point here is just 1 over Km 2 over Vmax. Yeah. And that's really all there is to that. And so this graph is actually a lot more convenient for thinking about the various different types of inhibitors that they make you learn about, and really any problem. Like if you get, as soon as you kind of like get even moderately comfortable at looking at this graph, it actually legitimately does become a lot easier to analyze any problem they're going to throw at you using this line of reasoning, especially because you're not given like a graphing calculator with nonlinear regression and all that stuff. So this is a lot easier to work with. For instance, I'm going to flip to the page where they've got this inhibitor table, because I loathe the way that they describe all of these inhibitors on this test. I mean, do you know what table I'm talking about? I don't know if you.
Yeah.
Just like
I do.
I hate the super ambiguous names. That's the problem I have with it. But it's just something. It's just one of those things you have to memorize.
Names of the type of inhibition.
Well, I don't know if it's ambiguous as much as it is like super duper similar and annoying.
Yeah, it's poorly named.
Yeah. Okay, thanks. I thought you were making fun of me.
No, slightly, but also I agree.
Yeah. Okay, thanks. Yeah. So this is the thing I'm talking about. This is stupid. This table. I just want the table.
Yeah.
Yeah. See? Like really just the names of them. Just that's the thing I have the problem with. Like competitive is fine. Competitive is great. Non-competitive is stupid. And the fact that there's a non-competitive and an uncompetitive is stupid. Actually, that's what I mean by stupid. Like that's the thing I have a problem with. Anyway, so this table is ultimately something you kind of just have to memorize, because it doesn't make a whole lot of sense either way that you want to think about it. And by memorize, I just mean you have to memorize what this one is and what this one is, really. So specifically, first, with regard to the competitive inhibitor, that's the one that's the most intuitively easy to think about. What's it mean by a competitive inhibitor?
It competes with what would actually bind to the substrate, so it takes up that active site entirely.
Okay, right. Yeah,
or it binds to the active site directly.
yeah, exactly. So it binds to the active site of the enzyme, of the empty enzyme. And so does that decrease the Vmax?
No.
Okay. Correct. Does it affect the Km at all? I had to think for a second. I forgot what I had asked. Yeah. So what's it? So why doesn't
because
the
it
Vmax
affects
change?
the affinity.
Okay.
Oh, why doesn't the Vmax change?
Right. Yeah.
Because the substrate can still compete for the active site.
Right.
So it's like if just like a bunch is there, it's like a stampede essentially. That's what I imagine.
Yeah, exactly.
Yeah, it'll still be able to run at like the same maximum.
Right. Yeah. It's like given a sufficient volume of or concentration of substrate, the inhibitor will eventually become negligible, and so it won't matter anymore. And so you'll still get there. So it'll look something like I this is the one that I kind of do like to draw more on this one, just because it's easy to draw it on this. on this
Mhm.
regular graph. So it's gonna look not like that. I just talked about how the Vmax gets to be the same eventually, but something like that. Not the best picture ever,
Mhm.
but I think you get what I'm saying. So that would be a competitive inhibitor. And so that's the only one that binds to the active site of the empty enzyme. The rest of these don't do that. They bind to other versions of the enzyme. So where does a non-competitive inhibitor bind? I guess we can start there.
Not the active site. It binds to the allosteric site.
Okay, so yeah, so all of these are going to bind to the allosteric site, but you're going to find there's like a excerpt in the textbook that, or whatever, review book, whatever they want to call it, that talks about a little bit more specifically than that, what they bind to. And this is the way to kind of memorize these without actually having to memorize. Like you can actually reason your way through it if you just memorize what each of these things prefers to bind to. And by that, you know what I mean? So by that, I'm meaning
Yeah.
oh, okay, you do. So like some of them will bind to the like the empty enzyme versus some of them bind to the enzyme substrate complex, and
Mhm.
whichever one you're referring to allows you to predict what's going on here. So all right, so which do you know which one the non-competitive inhibitors are? I don't think it says on it.
Non-competitive inhibitor is going to bind to an empty enzyme.
Okay, nice. Wait, this I thought I missed it.
Maybe.
Non-competitive. So the non-competitive inhibitors bind equally well to the empty enzyme and to the enzyme substrate
Okay, so it
complex.
does both. Okay, yeah.
Yeah.
But either way, it induces a change in the actual conformation of the enzyme.
Yeah. So I'm just gonna write binds to the enzyme substrate complex as well as just the enzyme, and that's about the same. Okay, and so that's really important because it allows you to predict what's going to happen to both Vmax and to Km. So minus my table for a second. What happens to the Vmax and to the Km of a non-competitive, or of like if we just add a non-competitive inhibitor? I can't speak either.
Sure. So in terms of Vmax, it's actually going to change it and decrease it because regardless of stampede or not, there wouldn't be enough available enzyme to bind.
Okay.
And in terms of K, it doesn't, because it's binding to an allosteric site, it doesn't actually reduce its affinity for the substrate.
Okay. So
That's my answer, I think.
So it doesn't. So you're saying it doesn't affect Km and it does lower Vmax.
Yes.
That's correct. Yeah, you're right.
Okay, cool.
Nice. Yeah.
You were making me doubt myself.
Yeah. So I was gonna draw a bunch of different lines on this and see if like tell me which one is right. But yeah, so it would look kind of like this, right? Because you're gonna have the same x-intercept and a higher y-intercept because it lowered Vmax, right?
Right.
Yeah. So that is the non-competitive inhibitor.
Yeah, I always forget that it's going to increase the actual, like where the y-intercept is because it's reciprocal.
Right.
I always assume it's going to be below, and that's where I get it wrong. Anyways.
Right. Yeah. Just know that that's the high, that this black line, the non-inhibited thing, that's the highest up that y-intercept is going, or I just did this thing. It's the lowest down that y-intercept is going to go on this graph. Yeah. Oh, come on. I wanted my table back. Whatever. The table kind of sucks anyway. So I just deleted everything. What just happened? Oh, I see. I think it's just down here. Yeah. All right. So so that's the non-competitive inhibitor, binds to the empty enzyme and the enzyme substrate complex equally well. What about the uncompetitive inhibitor then?
Uncompetitive will bind to the complex, so the enzyme substrate complex. I don't think it does both. Yeah, it doesn't do both. And in terms of Vmax and Km, well, it would lower Km because it's binding to the complex. So it decreases the enzyme's affinity for said complex. And I know it reduces Vmax, but I don't know why.
Okay. So you said it would do it. Which way did what was your reasoning for KM? What did you say it did to
Both would
KM?
decrease. Both would
Okay, both
decrease.
decrease. So it becomes higher affinity.
Oh
I'm
yeah,
not
it would
saying you're.
become higher affinity. If it's lowering the Km,
Mhm.
yeah, it would become higher affinity.
Does that make sense?
Not in this minute because I was just confusing myself to say the
Sorry.
opposite. No, that's fine. That was my mix up.
Okay, I just want to make
Okay,
sure it
so if
wasn't my
it's
fault.
binding to the enzyme substrate complex, it's making a conformational change that allows the competitor to bind. Increase the affinity. Like I just have that one memorized.
Yeah, no, but you're
Yeah.
everything you said is right too. I don't know what you said for the explanation because I was thinking through
No,
it
my
because
explanation was the opposite because I was saying that it
okay,
would
all right.
decrease the
I
affinity.
I thought it was, that's why I asked again.
Yeah.
But I
Okay,
just wanted
so
to make sure.
why would it increase the affinity? Even
Yeah, so it does increase the affinity. You're right.
yeah.
But it's just the fact that so whenever it binds to, if you think about like just draw the picture might make it help a little bit. So say you have this enzyme and it's also got I need to give it an allosteric site there. It's also got this allosteric site. And so the thing doesn't really care to bind to the allosteric site whenever the enzyme is empty. But now let's say the enzyme has its substrate. So here, it's full of substrate inside its mouth. And so that will change the allosteric site just enough that the inhibitor can come bind to the allosteric site. But now when the enzyme has a substrate in its mouth, maybe there's like some notches here that keep it from leaving or something. And so whenever the thing binds to the enzyme substrate complex, it causes this conformational shift that prevents the substrate from being able to leave the enzyme. You see what I'm saying?
Yeah.
Because the substrate's bound, but it's at this place where it could fall off and it'll come on and off with like, I don't know, relative ease in both ways. But this thing causes another conformational shift with the substrate already bound that basically, like I drew that, I think it's just up here. This initial, this equation right here, this thing. So what it's doing is and this is uncompetitive, right? Uncompetitive will lead to a increase in K1
so that means an increase.
Yeah, and decrease in K-1, right?
Right. So there's more reactants of enzyme substrate available now to form.
Yeah, but it's also going to decrease K-cat too. Because we're not going to make more product. We're just keeping the enzyme substrate complex.
Right.
It just stabilizes the enzyme
increasing
substrate complex, basically.
Its efficiency.
Well, it decreases the efficiency. It definitely decreases the efficiency.
Okay. Yeah.
Right? Because it can't finish the job. So like overall product made is going down. We're just sticking it here.
Oh, right. Okay, because if it conformationally changes, then it can't. Okay, yeah. Okay.
Right. Yeah. So what I was saying with this stupid little picture down here is like maybe the enzyme substrate complex without the inhibitor. So if the inhibitor is not here, then the enzyme substrate complex maybe just looks like this. See what I'm saying? So it's just like a wedge, and then the blue thing can leave whenever it wants. But say this thing comes in and binds, it maybe causes conformational shift so that now we have these notches or something. It's
Right.
kind of overly simplistic, but like now it can't get out as easily.
Yes.
It's like tire spikes. Yeah.
That makes sense.
All right. So what's its graph going to look like compared to the others on here?
Well, if Vmax is lowered, then the y-intercept will be even higher. And if its Km is changed and also lowered, then it'll also be moved towards the right.
Yeah. Okay. I had to think for just a second. I was like, wait, what? Yes, that's correct. Yeah. So it ends up looking kind of like this.
Yes.
Yeah. Yep. That's true. And so one thing you could be aware of is that it will necessarily always diverge from the original line. My screen just went black when I went to write that. So like these two lines, that didn't work out. This line and this initial line will always diverge from one another. They're never going to cross on the right side of the y-axis. Not possible for them to cross on the right side. That makes sense. Versus well, and I guess the blue line and the original line can't cross on that side of the y-axis either, but the red line and the blue line can. Yeah, because this would also be accurate. So yeah. Anyway. Yeah, so that's it for the inhibitor stuff. That's it. But that's why I wanted to go over that inhibitor stuff, just because it is a little bit confusing. But once you think about it from that perspective, like if it binds, and so I guess actually we didn't talk about the mixed ones yet. This might just drive it home a little bit. So you've got some mixed inhibitors okay, so for mixed inhibitors, you've got some mixed, here, I'm just gonna write it. Mixed inhibitors, and you have some that prefer the enzyme substrate complex versus others that will prefer the empty enzyme. And so based on whether they prefer the enzyme substrate complex or the empty enzyme, that determines whether they will increase or decrease Km, but they will always decrease Vmax.
Okay. That makes sense. Yeah. Or they will always decrease Vmax. Yeah. You said that. Never mind. I heard increase, and that was really stupid.
Yeah, so always decrease Vmax, but Km, or you can say effect on Km, depends on whether it prefers the enzyme there. Okay. So this one, so if it prefers the complex, what will it do to Km?
If it prefers the complex, it will decrease Km.
Yes.
Okay.
Nice. And then this would obviously
increase Km.
Nice. Okay, cool. So and I think that I hate the names of those inhibitors so much. Like they're just not super descriptive at all. Non-competitive and uncompetitive just drives me nuts. But anyway, so that's how to think through that. Let's see, what else could we talk about in this stuff? I guess you do have to go in like 9 minutes. So
is there anything else you wanted to cover today specifically, or is this like the most important, you would say?
Yeah, we've definitely covered the most important stuff for today. Okay, yeah, the only other thing that I would talk about, I just fortunately turned to the exact perfect page to remind myself that it's covered later, so I don't need to talk about it right now. So yeah, it'll be covered next in the stuff you do for next time.
Oh, here's a question that is very general and tips on memorizing the amino acids. Because I had to do that for BioCAT, but now it's been like 2 years. And I remember some of them, but not all of them. Yeah, any recommendations?
Yeah, my general method for anything like that is just a kind of a brute force approach where you just like, so a lot of people
Nice.
make flashcards. I hate flashcards personally. I just don't like them. I lose them and they don't go into binders well. And so it's mostly my organizing that doesn't like flashcards, but for whatever reason I hate them. So I will tend to, so what I'll do is either get like a marker board or chalkboard or something. This is what I did in undergrad, but in med school, whenever I had to memorize large things like that, and I did all the time, is I would just like get a big stack of like printer paper, and I'd use printer paper just because it seemed better, not having the lines across it
Fair.
and stuff. And then I would just draw them all out over and over and over again.
Okay.
And depending on how many days I had, obviously for this one, you won't have to go that hard on it, but you could have them memorized by Monday if you wanted to, like if you wanted to
Yeah.
do that. And I would just like make myself draw as much as I could from memory and then check it. And then,
All the time.
like just like over time playing that game, you end up getting it. It's just, I think that I don't know that there's a lot of really good tricks.
No, that's fair. I think
Maybe,
that's like mainly what I did last time, actually. I mean, there was a time where I was just not figuring out and kept reading it over and over again, but I
yeah.
found that that didn't work anyways.
Yeah.
um, yeah. Okay, cool. I'm glad
Yeah.
that.
And you could also draw it out. Like, I think one thing that I eventually did at one point, because I've had to memorize these multiple times. I think at one point I just started drawing it out like an R and then whatever the side chain was. So like if the amino acid was
Mm,
splicing, I would just do that. Like pretend like the R
yeah,
rather than being for the R group, it's like flipped on its head so that
right.
the R
Because
is
it's
like
all
the
the
rest of
same
it.
anyways.
Yeah,
Yeah.
because the rest of it's just the same except for just like a couple of them, like histidine and
Hmm.
proline, I think. But for the rest
Hmm.
of them, it's the same. So that's my recommendation. I wouldn't worry too much about it right now. Although that said, it's like the sooner you get it in your head, the better
Yeah.
the practice questions will feel. This is something that Omar and I went back and forth on the whole time that he was prepping because he took a lot longer. He put off memorizing all the equations way longer than I wanted him to. And so we were just like kept trying to urge him to do it. And finally, like right at the end, once he finally had them memorized, he was doing some practice questions and he's like, yeah, this is so much easier. These equations memorized. I'm like,
Yeah.
yeah, I know. That's what I've been trying to tell you because it just like I told him to memorize, or I always tell people to memorize the equations sooner rather than later because they're going to affect every level of reasoning you have on the chem phys section of the MCAT. And
I
so
was gonna put
versus,
it off too.
yeah, no, don't do that. The the
Okay.
amino acids you can put off. You can put that off until like I don't care. Like I
Okay.
could probably actually I know it. So last time I took a practice MCAT, which was 9 months ago, I hadn't even thought about an amino acid in 6 months and hadn't had it memorized in like 3 years. And I got a perfect score on biochem, and chem phys. And so you don't have to know them, but what's
It's
more
better.
important than knowing them outright is knowing like the trends, like which ones are acidic, which
Hmm.
ones are basic, like is it likely to be protonated at a certain pH or not? That's the most important thing. And like which ones are going to cause, like if a region of a protein has a whole bunch of, I don't know, if a region of a protein has a whole bunch of alanine,
Hmm.
where is that region of the protein likely to exist when the protein is in vivo versus if it had a whole bunch of like glutamate and lysine or something,
Right.
right? Yeah, because so like the alanine one is going to be largely internal to the protein, and the glutamate and lysine is likely to be external to the protein because the protein's likely dissolved in water. So anyway, stuff like that. That's the kind of
Okay.
stuff they care so much about, that general sort of thinking. Anyway, I will let you get going because I know you need to leave and you've got like 3.5 minutes
Give
left.
give me reading first.
Oh yeah, shoot, sorry. It's just gonna be a continuation of this,
Or
or you
don't.
can
I'll have a freebie. I won't do anything.
Yeah, it's basically, so what we're going to be doing here is just going through the OChem and biochem together. Probably and I would recommend, okay, so for this next one, I would say 5, 6, 7 Ochem and 5. I'm so torn on that. Actually do like 5 through, sorry, I'm thinking 1 second. Because I made this mistake before. I almost did it again. I realize it now. Okay, so you want to do 4 and only 4 on biochem, and and 3 since you didn't get to it. But I don't think 3 is a huge chapter. 2 is the primary chapter from this front part of the biochem stuff. Anyway, 4 on biochem, and then like 5 through 10 on ochem.
Okay.
Yeah, that'll be perfect. Yeah, actually, and then 12 also if you get to it. Don't worry about 11 just yet. I have a way of tackling that you'll probably not even end up using the book for 11 because it's terrible.
Okay.
Like their spectroscopy explanations are ass. And I stole some stuff from from DAT bootcamp that is way better. So yeah. Anyway.
Okay.
So it's like DAT prep material, but they have to know more about it than you guys do. So I've kind of adopted it. Anyway. Yeah, so
Beautiful.
we'll put off
I'll get
that 11.
done.
Okay, awesome. Sounds good. And let me know if you have any questions, obviously. Otherwise, I will talk to you on Tuesday. Have a good weekend.
Sounds good. You too.
All right, thanks. Oh, thank you. See you later.